So, welcome everyone. I'm glad to see so many of you actually came in and just registered on the meetup. Hi guys. I see a lot of familiar faces as well. Those of you who don't know me, I'm Norby. I work across the street. I can draw you a map if you have trouble finding it. I hope that some of you saw my cartographing skills on the meetup page. I work for Novum. It's a Swiss company. I'm not going to talk about that right now. If you have questions about it, feel free to ask me. However, in Novum we have something called ADN RETS. That stands for Novum Regular Advanced Training Sessions. Unfortunately, I cannot take credit for this awesome acronym. That goes to Yuri. He will do the second presentation. Basically, it's about some topics we pick, and we try to go in depth into those and give some presentations. And I originally did this presentation a year and a half ago, so it might be rusty in some places, but we'll see. The reason I wanted to do this is because I see that lots of Java developers think of the JVM as some black magic thing, that you give it a class file and wow, outputs a hello world or something. And I don't see this as being a beneficial thing, because if you know what's going on behind the scene, you actually gain power, and this power can give you the edge you need over your competition. You might think of this as, oh, okay, come on, this is premature optimization. Everyone knows the famous quote. Probably this is the single quote that every IT guy knows from Knut. Yeah, premature optimization. Since no one raises his hand, that already means that you don't agree with this quote. I'm happy to see that. Zoli, stop smiling. So actually what I want to emphasize here is that this is not about premature optimization. It's about avoiding known problems. So writing dumb code is not an excuse. So this is why it's important to get the necessary know-how. For that, I'm going to talk about the hotspot JVM. From here on, when I say JVM, I mean Oracle's hotspot JVM or the OpenJDK, not something else like an Azure implementation or something. That's a completely different topic, so bear in mind. And I said that we are going to talk about the JIT compiler, but first, before we get there, we have to talk about the runtime part of the JVM, because that's how you get to the JITing part. The runtime part is actually very complex. It does tons of things. Like you see a wall of text there, feel free to read it. I don't expect you to do so. What I expect from you is just to get the overall big picture. However, when we start our application, the first thing it does is it interprets it. So if you have a class file that you wrote, that's essentially a text file, you compile it with the Java compiler, you get a stream of bytecodes. So the interpreter executes those bytecodes, and how it does it is quite remarkable. In IT or computer science terminology, it's called the template-based interpreter. Yeah, it's a fancy name for a lookup table that contains machine code for the CPU you are executing for. However, it generates that machine code templates when you start the JVM, and it's actually quite huge. How it works is, like a CPU, you have an instruction pointer. Now it's called bytecode pointer. You pick something from the lookup table, you fetch the machine code that needs to be executed, and then you start executing it step by step until you get to a certain point where you fetch the next instruction, then do again all the same thing, and at the end jump to somewhere else like function call and so forth. You get the picture. If you want to find out more about this functionality or how the interpreter works, there's a JVM flag that you can pass to your application, and it will print some details for you. Talking about flags, what flags are actually? These are configuration parameters for the JVM. You have two large categories in essence. Boolean flags, yes, no, and value flags. You set both the same way with the -XX, and you list the parameter name. if you want to dump all possible configuration flags for the JVM, you can do it with the print flags final parameter. This will give you all the possible configurations. Can you guess the number that it will give you? I mean, how many configuration parameters do you have? Anyone? Give me some numbers, come on.
1,000.
What?
1,000.
1,000. Anyone else?
That was close.
We have a winner.
Thank you.
When I did it first, I checked it for Java version 1.7, 675 flags. Have fun reading the documentation for all those flags. You think that it would get better and that engineers realize that, yeah, probably we need fewer. No, that's not happening. We got more. So, yeah. This is how it looks like. Usually, let's say some GC entries you can grab for it using Linux, and you see that you have these flags with some default values. How that's possible? We only gave a single flag. Where do those values come from? Yeah, the fancy name for default values under the JVM, ergonomics. It's actually a tricky bastard because you would think that you have more or less the same default values across all platforms, but no. Depending on the operating system, depending on the JVM version, and of course depending on the CPU architecture, you get a different set of configurations. So you might test your application on your own workstation, ship it somewhere else, and it will have a completely different profile because you relied on ergonomics. And what's the best thing about this is that they tend to change even during minor releases of the JVM. Just some surprise for you, so it's better to check the official Oracle documentation. If you try to grab for this flag that solves all your problems, unfortunately it's not there. So what can we do? Well, this is where the JIT compiler comes in. Those of you who are not familiar with this terminology, it essentially follows the Pareto principle, meaning the 20-80 rule, if you know it by that way, that your application has a certain set of bytecodes that are executed frequently. Those bytecodes will get compiled to optimized machine code. The JVM has two tools for this, the C1 and C2. These are two compilers, so you can guess what the C stands for. The C1 is the eager guy who will jump at the given moment to generate some machine code as fast as he can. Yeah, you will get something. It will be faster than the interpreter. However, it's not going to blow anything out of the water. Then you have the C2 guy who's kind of laid back, takes his time, gives you some machine code, but that will be really something. If you start your application, depending on which compiler you use, it either looks like a bit of interpreting, a bit of profiling, compilation, then executing the machine code. And you can see that in case of C2, it takes a bit more time to compile, profile, and starts executing the machine code at a later stage. Now, when should you pick which one? It again depends on your requirements. Usually if you want fast startup time, C1 is your choice. If you want, I don't know, you have a web application that will run for decades, the logical choice would be C2. However, if we think about it, why do we have to even pick one? Shouldn't it just sort it out? Fortunately, it has this feature for a while now, the JVM. It's called tiered compilation. Essentially, it juggles between the two compilers. By default, it's now the default solution in Java 8. Before that, it was also available in Java 7. However, it was not the default. You had to enable it manually. How this works is it will start compiling your application with C1, and when the JVM has additional information about your application, it will switch to C2 and compile it natively and just replace the implementation that's running. The tiered compilation actually has different levels, so from 0 to 4, ranging from interpreter to very optimized code. Yeah, these are numbers. I have a more graspable way of seeing these things. Now, who doesn't know which cartoon is this from? So we have a single person in the audience who is not familiar with Dragon Ball. Now go home and watch it. Leave immediately. So you have the interpreter, that's essentially Krillin. If he's not too busy being dead, he will do something for you. When things are getting a bit difficult, then you have Goku. And when things are really bad, then you have Super Saiyan level 4. So let's get back to the idea. So these are the tiers you have. The JVM has a typical use case. First, it sends in Krillin. Then it immediately switches to a more powerful Super Saiyan. And when it sees that, yeah, you really need the performance, then it will give the job to the compilation job to the C2 compiler for you to get an efficient code. Now, this is a typical use case that's not always possible. The reason for that is that you have background compilers, background jobs for the C1 and C2 compiler. Depending on how many you have by default, if you didn't configure it, the compilation queues can be full. So if, let's say, the C2 compiler is not available, then what the JVM will do is, yeah, I have the C1 compiler free, let's just generate a bit more efficient code using that. And until the C1 queue becomes available, then we can churn out top performance codes. Now we learned about C1, C2 tiered compilation. Let's just see a bit of comparison here. So these are done on some basic applications, not too sophisticated. I just want to give you the big picture. So if you have a simple application like a Hello World, you can see the client, server, and tiered compilation performances. As you can see, it doesn't matter there. However, when you get to some bigger applications such as NetBeans or Eclipse or some bloated IDE, then the thing starts to matter. So for client, you have faster startup time than server. That works. However, as you can see, tiered compilation is kind of in between the two. And for really huge applications, it doesn't matter because the I/O is the bottleneck. For batch applications, which essentially do a fixed amount of job, depending on the size of that job, it again falls back to the same setup that after a while, more or less, the tiered compilation is the winner. Now there's one interesting thing here, is that it's faster than the C2 based setup. The reason for that is that tiered compilation has a certain characteristics that there are some code spots where the JVM would say that I'm not going to compile that with a C2 optimizer, but that will still trigger for the C1. This is why you can see cases where the tiered compilation outperforms the server setting, but by default, usually they are on the same level. And last but not least, web applications. This is actually done. Here I did a load test that ran for a minute. The interesting outcome here is that the minute is more than enough for the JVM to warm up and optimize the code. So you can see that the server and the tiered compilation performance is not improving significantly if we give more warm-up time for the JVM. Usually if you are working with performance tools for JVM, they have a warm-up time because you have to kind of enable the JIT compilation. So this is why micro benchmarks are not necessarily the good way to check Java performance if you're not using adequate tooling for that. Now I've been talking about, okay, we are going to optimize the hotspots. How does that work? In the JVM, the methods are hot. That's what gets measured for frequency of access. Each method in your application has two properties, more or less. Two counters to be more precise. One for invocation, so how many times the method was invoked, and one for checking the counters of the incrementations inside the method body. So how many times you iterated through a for loop, for example. Let's just see a quick example here. I have the function and the other function. So the D function, the first function calls the second one, like we are going to just iterate through a couple of times, and do something on the other function where we are going to iterate again. So we started by calling the first function. the invocation counter increases by 1. Then we iterate the loop, so the package counter of that function increases by 1. Then we get to the other function, since we called it from the first one. There we get an invocation counter, and there we start iterating again, so package counter. Back to the first one, you get the picture, we call iterate, so the counters are going ahead. Now imagine that I click this thing a couple of times. Whoops, we reach the magical threshold, where the counters are aligned in such a way that the JVM has decided that it's about time to optimize this away. Now, what will happen here is that it will send this to a background job that will generate machine code, and on the next invocation, it will start using the native implementation of the function instead of interpreting the bytecode like it did before. That's awesome, but let's think for a moment. You have these micro benchmarks and applications where you just have an infinite loop running that will never get optimized by the JVM. Fortunately, it's not the case, because otherwise the JVM would suck at micro benchmarks. It has a feature called on-stack replacement. That's magical, really. I cannot say it any other way. So while you're iterating in a loop, it will figure it out that, yeah, I reached that magical threshold. So if we're going to compile that loop body, and for the next iteration, it will swap out from from interpreting the bytecode to actually executing native code. If that's not magic, I don't know what else is. So if you want to see how this works for your application, there's a simple flag to do that. It's called print compilation, and it will give you a dump of information that you can process. So you have a timestamp which gives you when your method was compiled. You have an ID which allows you to track to the compilation job that happened. You have some flags that specify what kind of compilation happened. Now there are like 5 flags here. The percentage sign is here in this example. That means on-stack replacement that I classified as magic beforehand. Besides that, here are the Super Saiyan levels that you can see that, okay, it went with C1 compiled until level 3, then at later stage it switched to C2 for level 4. Now, the other thing is that you can see what gets compiled. The important part here is that you see some code sizes there. That's the size of the bytecode, not the generated code. This is important for 2 reasons. One being that you have a fixed amount of code cache for your application, meaning that there's just a certain amount of functions you can compile, not everything. The other thing is that when it comes to advanced optimizations, you will see that the size of a method really matters. The other thing that it also does de-optimization. So based on profiling information, the JVM might decide that it can further optimize generated machine code, and it will do so. I mentioned that you have a certain limited code cache, but if we just check the counters and if the application runs for a long enough time, it would compile everything. To counteract that, the JVM has so-called, let's say, cooldown timers as well, where it goes and decrements these counters at a certain set of intervals. This will lead to 2 things: that you will have lukewarm methods that are not called frequently enough to be optimized away, and the other thing, that some things can be de-optimized over time or thrown away over time. Like let's say that at application boot up you do a lot of crunching, number crunching for whatever caching pre-calculation, then you are not going to use that at all at a later stage. The JVM will just throw that away after a while. You can use the compiler threshold to fiddle with these 2 counters. I would say, there isn't really an exact formula that you can use to pinpoint, okay, now this is going to get compiled. You will find some rough formulas in the documentation, but it's enough to get you started. Usually you either decrease it or increase it. Now, so far we've talked about basic optimizations. There's one additional thing called advanced optimizations. There are a couple of them actually. sec. Meanwhile, you can look at the lovely point implementation. So it's quite common that we have POJOs in our applications, and we have getters, setters, because those can be generated, and yeah, those are OOP principles, and everybody loves getters, setters. However, in the early days of Java, they said that no, you shouldn't use those. Those are performance penalty. That is actually true. However, not nowadays, since inlining takes care of that. So the JVM will see, yeah, that's like a single instruction. I will just inline that, so you won't pay for the method invocation price for those functions. Inlining is actually the most important optimization in modern languages, not just the JVM. Try disabling inlining and measure the performance of your application. You will be surprised. Unfortunately, there's no exact way to check what's inline and what's not. There's no parameter for that by default. You have to build your own JVM with debug settings to get a print inlining flag that will tell you what got inlined and what didn't. Makes complete sense. However, you do have two parameters that you can fiddle with. One is about inlining frequently called methods. That's the first parameter, the maxfrec inline size. The other is about inlining below a certain set of size threshold. By default, usually the settings are perfect. You can try fiddling with these, but it's not advised. Maybe this is the reason why they don't provide the print inlining option by default. There's another advanced technique for optimization. It's called escape analysis. That's a huge topic because you can escape analysis everything. As you can see, you have object explosion, which is about, okay, I'm not going to allocate that, I'm not going to produce garbage. You have scalar replacement, which says that, yeah, this thing is used frequently, I will just put it in a CPU register instead of fetching it from the memory each time, because that's very slow compared to a register. You have thread stack allocation. In Java, you don't get the choice of deciding where you want to allocate a variable, whether to put it in a heap or on the stack. So this optimization helps you in that area, that when it sees that it's not going to escape a local method or something, it's just going to put it on the thread stack. And of course, the same goes for synchronization. The JVM can actually detect whether a variable is accessible by multiple threads. If not, it will optimize away the synchronization, because those are actually expensive operations. The JVM itself does tons of optimizations when it comes to synchronization, because those are really not cheap operations by default. And yeah, the same goes for garbage collection. Let's see an example how this works. Let's say I want to calculate factorial numbers. Because I'm a lazy programmer, I'm going to evaluate it when that's really necessary. Let's say I want to calculate the first 100 factorial numbers. I will just write a loop, iterate 100 times, pass in the loop counter, calculate the factorial, that's it. And what magic happens here? So I create a factorial there. That's only referenced inside the loop, the for loop. Now, the JVM will see that, and it will determine that that variable is only accessible by the current thread. So it's just going to optimize away the synchronization. We don't need that here. It will realize that actually I'm using that factorial number quite frequently, so why am I fetching it each time from the memory? Why can't I just put it in a register and I have access to it immediately? Like there's a two order of magnitude difference between the memory and the CPU register. It does that as well. Meanwhile, it actually realizes that you don't even need the whole object. What are we storing here? Just the calculated value which is a big integer. Why would we store the whole thing if you only need a part of that object? So it's just going to throw away the object and use the necessary fields inside the register where possible. And this gets more and more complicated. There are tons of blog posts, presentations, focusing on advanced optimization techniques and whatnot. So I'm telling you now that when you're writing an application where you have no clue how it should work, you also have to focus on these things. Like that's going to happen, right? Who will do that from now on? I failed. Not even one hand. But I was expecting this, you lazy bunch, so I'm going to just give you one suggestion. Write small methods, that's it. Inlining will be your friend. Method hotness will be your friend. Escape analysis will be your friend. Automated testing will be your friend. Each of these things will become a lot simpler. Now, what's that certain size for a method? Think of a number that's too big. Smaller ones. Try to use functional principles here. If you are interested in this topic, I can really recommend these two books. They are not easy to read. Really not easy, especially the second one. That's like terrible. That lots of information crammed in every single line. But it's really an awesome book about the subject. It even goes into Java EE specific optimizations as well. Questions? Yes, we have a point. Yes, please. Yeah, that's a good question. It's actually, so I'm going to repeat the question. Thanks, Julie. Am I talking about Java 8 or specific Java implementation, or these are generally true for various JVM versions? These are actually true for various JVM versions. Most of the things that I listed here are in Java 7 as well. Some of them are in Java 6. Lots of optimizations have been done for Java 5 as well. So more or less you can rely on these things in, let's say, a decently up-to-date Java applications. I'm talking like Java 1.6 and upwards. Yeah, they are adding all the time newer and newer optimizations as well. You can check the detailed release notes for various JVM versions, and you will see that they now have partial escape analysis and whatever. So things are getting more and more complicated in this area as well. Zoli?
Yeah, so I saw that there were different tiers for C1. So there was simple compilation, full compilation. Can you elaborate what kind of differences that mean?
No. So the question was whether I can elaborate what are the main differences between the multiple levels of the C1 compiler. No. Now, to be honest, I can guess things. I would say I wouldn't go into guessing it. I'm not aware of the exact differences.
Could it be like with C compiler with various optimization tags?
Yes,
so
something. Yeah.
Just dump it into assembly code and the other ones.
Yes, that's true. More or less, that's true. So the C1, you will immediately generate some machine code. You can actually. It's nice to check what the generated code looks like, and you will see that the size dramatically decreases. It tends to do more type-specific optimizations as well. Do better end registration. So use all the registers at the most efficient way. These are no, it's okay, that's a bit general. When it comes to compilers, especially JIT compilers, end registration is the process of allocating using all the registers available at your CPU. Mapping them the more efficiently means more performance for you. There are tons of algorithms on how you can do that, and for this is the case where the different compilers comes into place. When you have more profiling information, you can do better decisions. More or less, that's it. You can do a talk about the differences. I like that idea. Yes?
If we have time, I have two questions. One of the first one is, when is the first year of C1 optimization used? On your slides, I was missing that. The other ones were used.
Yeah, that's again a good question. That depends. The JVM tries to optimize after, let's say, it has enough profiling information. It again depends on the characteristics of your application. So it might be used when when, let's say, for example, the C2 compiler queue is busy, but there are tons of jobs lined up for doing compilation. So instead of doing too much optimization at the first time, it will try to compile more at once using simpler optimizations, because that leads to faster compilation.
And do you have any experience on the architecture called X32, on which your memory module is reduced to 32 bits, but you are having access to 64-bit registers?
Yeah, that again. So the main question. So the question was that, do I have experience when it comes to CPU architectures where by default the word length is 32 bits, but you have 64-bit registers? Actually, that's a common thing. Lots of CPUs have larger registers when it comes to accumulators. The JVM will try to make use of those. Actually, that's in the specification, to make use of how it will make use of that, whether it will split up the register to two parts. That again depends on the implementation. What the critical point there is how we configure the JVM, so how the pointer addressing is made. So by default it should be 32 bits, so yeah, that should work more or less in an optimal way. If, let's say, you enable the compressed OPS, I'm not even sure what that stands for right now. So the object pointers, whether it should point to 32 bits or 64 bits, that can have a bigger impact on the performance in these situations. Yeah. So do we have other configuration when it comes to inlining? Write small methods. That's the only way you can. I'm sorry to say this, but that's the only way. Final can encourage other optimizations, but inlining is really out of your hands.
And also with inlining, if your method is too big, then the compiler will say, yeah, I'm not even going to try inlining it because it's too big.
Yeah, that's a good point. Inlining is actually a double-edged sword. So if I'm going to say, yeah, I'm just going to inline everything, that will make it fast. No, that will make it damn slow. Because it's important that you have cache alignment, you have a certain size of cache, so that it has to be an optimal size to make the most efficient use of the available resources. So this is why I said that even in the books that I mentioned, they usually say that, yeah, don't play with those values. You can try, but these are the most optimal values that you can find in general.
I think the default is about 80 bytes. You want to be more specific.
35 bytes for the size and 350 bytes for the hot methods. Yes? Yeah. Yes, exactly. Because let's say you have a huge object like a God class that we tend to write that has everything, and you only use 2 fields of that class for that. Then it will only use those 2 fields. It won't allocate the whole object. It will optimize it away because those are unused variables when it comes to the code. I would suggest that if you have further questions, feel free to ask me, but the food arrived meanwhile, so if no objections, then that's it. Thank you for your attention.